Hello, here we are continuing with our materials questions. We've got atoms in a solid held in position by electrical forces. These electrical forces can be represented by imaginary interatomic springs between neighbouring atoms. Okay, these obey Hooke's law as a force constant, just as a normal spring in the laboratory. Researchers in America have recently managed to determine the force experienced by an individual atom of cobalt when the atoms are squeezed together. Researchers have found that a force of 210 piconewtons changed the separation between a pair of atoms by a distance of 0.16 nanometers. Okay, so they're just trying to throw you off a bit by moving away from the usual spring scenario and then throwing in some really small numbers here and seeing if we can remember what picos and nanos are. We got to start by stating Hooke's law. So Hooke's law is that the extension is proportional to force applied as long as we haven't gone beyond the elastic limit, so within elastic limit. So yeah, for Hooke's law is that proportionality rather than actually writing out the F equals kx. So that's Hooke's law. Calculate the force constant of the interatomic spring for a pair of cobalt atoms. Right, so our force constant, that is going to be F divided by X. So our force is 210 piconewtons. So pico is 10 to the minus 12. And we got to divide that by 0.16 times, and this is nanometers, that's 10 to the minus 9. So we've got a 10 to the minus 3 on top. So let's get rid of all of that, and then we can drop this 210 back to 0.21. All in all, that's going to be a 0.21 over 0.16 by the time we've dealt with all of these tens. And now we can just stick that into we haven't quite got a simple. It's going to be about 1.3 or thereabouts, isn't it? 21 divided by 16, 1.3125. And we're at two significant figures as usual. So 1.31 equals 1.3 newtons per meter. Two significant figures. So that's all fine. Figure 7.2 shows a stress against strain graph for a metal wire up to its breaking point. Use the graph to determine Young's modulus of the metal. Right, now, I find these ones interesting when you see a lot of mark schemes who insist on taking gradients, and they'll put on this, make sure you've taken the gradient over the widest possible range and all this sort of stuff. Well, Young's modulus isn't a gradient. We can use the gradient, particularly when it is an approximated line. If we've got measurements on there and we're doing a best fit, then the gradient is great because it throws in a sort of averaging effect to get our best fit Young's modulus. This gradient is straight as an arrow, so it's not really going to matter where we pick. You can just pick a point on there and divide the y value by the x value because that is what Young's modulus is. So really, it's nice to pick out one which is going through a join, an actual intersection of the coordinates. So somewhere like here, you can have any of these. There's another one there. So there's quite a few of these where you can see them. I mean, of course, they're going to be regularly spaced up here because that is, it's a straight line. So we're going to see this thing recurring over and over again. I mean, it happens that we do have a really nice one here at the end of the straight section. But one of the problems of taking the gradient over as large as possible area, you have to, at some point, decide where the straight section has finished. I mean, is it actually finished here? I mean, this is at 7 times 10 to the 7 and then 0.8 times 10 to the minus 3, or has that already started curving? I mean, you're getting into other areas here. So I think their insistence on doing gradients all the time with Young's modulus is somewhat overstated. So let's go for, let's go for this one. I mean, it's going through 3 here. So we've got 3 times 10 to the 7 for our y coordinate, and then this is 1, 2, 3, 4, 5 will be there. we're coming down on that one, so that'd be 3.4 times 10 to the minus 3. So we're going to get the same, whatever value we're going to get is dictated by the accuracy of reading one pair of coordinates, not on a gradient. It doesn't make any difference because we know we're going through the origin, so it's taken that uncertainty out of the picture, out of the whole equation, so to speak. So yeah, putting this in, then we've got I can't even remember what I said, the numbers. Oh, that's 0.34. So that'd be, I've just moved that up a little bit. So that'd be 10 to the minus 4 now. So we're going to have a 10 to the 11, although it'll drop back down to 10 to the 10 again when we put in this 3 divided by 3.4, 0.882, etc., etc. So 8.8, so take back one of those 10s, times 10 to the 10 pascals. Yes, so then we've got the wire breaks when a force of 19 newtons is applied. Use a graph to determine the cross-sectional area of the wire at the breaking point. Right, the breaking point here, so this is our stress, that's our force over cross-sectional area on there. So we've got the 6 times 10 to the 7, because that is our stress at the breaking point, must be 19 divided by the area. So if we do our 19 divided by this, well, actually, well, we can see that is going to be 3 1/6. So that is going to lead to A is 3 1/6, so 3.16 recurring, so 3.2. And then we're going to have 10 to the minus 7 on this because we're dividing by that 10 to the 7. And that is meters squared. Yeah, so that's not a bad question, but it's nice to think about that thing with Young's modulus and not, they have some weird stuff in some of these mark schemes, and I always think that's one of them. And now we've got another stress strain graph for two materials X and Y up to their breaking points. Right, so they've shown those. Put a tick in the appropriate column if the statement applies to the material. Right, we start off with this material is brittle. Okay, I'm going to come back to that for reasons I'll get onto at the moment. This material has a greater breaking stress. Right, so this is when they're breaking. Well, clearly Y has got a greater breaking stress than X because it's further up the Y-axis. This material obeys Hooke's law, right? So that's going to be if we've got a straight line going on. So that's only going to be for X. Right, brittle, and this is one of the problems we're going to get into here with the whole section on materials, is it's a little bit half-baked when we're dealing with all of this before we go off to university, and then quite possibly then you don't even necessarily look at materials again when you're studying as an undergraduate. And there's a problem with the terminology that we have and the way we describe materials and then what is expected in questions such as this. So brittle, really, we're talking about materials which don't extend very much before they snap. So they're starting at a particular length. They extend a tiny amount and then they're going to break. These are our brittle materials, things like ceramics and, well, ceramics are a good one, glass, things like that, some metals. But you've also got a lot of metals which don't behave in that way, and these will be, you get the ductile ones, these ones where they might start off looking a bit like X, but then they do all these weird sort of things. You get all this strange behavior going on where you're getting these big extensions with very little increase in force. So you get your ductile ones. These are ones, quite often the brittle and ductile, you can think of them with plasticine. If you played around with plasticine, once you've warmed the stuff up, you can stretch it out. It becomes quite malleable. It's quite ductile. You can reshape it and things like that quite happily. But if it's old or it's a bit cold or whatever, then it might extend a little bit and then it will just snap. It will be quite brittle. so we've got these descriptions. Now, the issue I've got now, coming back to this first one here, with which ones of these are brittle. Well, X, yeah, we're happy with X being brittle. It's extending a small amount. I mean, we don't have a scale on this axis here, so we don't know how much extension, but it's clearly got less extension than Y. And then it snaps, it stays Hookean, stays within an elastic limit. We've got a straight line, and then it snaps. So we can definitely tick here. Now, the thing with Y is, I mean, we're conditioned when we're studying, if we're doing A level or equivalent, that our brittle materials will be obeying Hooke's law, in which case we won't be ticking Y. But in terms of what we're really meaning by brittle, particularly on these scales where they're, we don't know how much of an extension this actually is. We don't know what this strain is here. Okay, it looks as though it's about 3 times or slightly less than that, 3 times the extension that we've got for X, but they could still be very small extensions, and then it just suddenly breaks. So for all intents and purposes, I mean, this isn't a far off of being a straight line. Whether we'd be able to tell between X and Y very easily in its behavior as to X is brittle and Y isn't, I think is open to debate. So you could have a sort of tentative tick in Y as well of, well, maybe that is brittle. We don't really know without some kind of scale here on the X-axis. Then in terms of our use of brittle as a word, as a description for a particular material, then maybe Y is. In terms of what is expected of us when we're doing exam questions, then, well, is X, because X is the one which is obeying Hooke's law, but we've then put that down here. And usually when you get these graphs which are going a bit more curving in the opposite direction, these would be our rubber and things like that can go this way, but you can have brittle rubber. You can have some rubber which is got sort of old and crusty, and you extend it a small amount and then it snaps. So maybe that's brittle rubber. So I would say this one here is open to debate as to whether Y is brittle or not. But yeah, you get some issues with this. There's a lot of terminology in materials, and it's not entirely clear. It's not unambiguous what a lot of these words actually mean, and I think that's a case in point there with brittle. All right, well, let's crack on anyway on to B. Kevlar, one of the strongest man-made materials, used in boat hulls, aircraft tires, bulletproof vests. That's the famous one, I suppose, for Kevlar. Sudden impacts cause the material to undergo plastic deformation. And explain what is meant by plastic deformation. So plastic deformation is where you've got a permanent extension to the material. So there will be a permanent extension once the stress or the force has been removed from the material. There will still be an extension. So these are the ones where you get your stress strain graph. It might come out and do something, although like that. So once you've removed your stress and you've gone back and hit the X-axis here, as in the Y value is 0, your stress is 0, you've got this now permanent extension on the strain axis. So that is your plastic deformation, that you have a permanent extension once the stress has been removed. Now we've got some calculations. One particular type of Kevlar has break-in stress of 3 times 10 to the 9 pascals. They've done this to 3 significant figures, which is unusual. Young's modulus of 1.3 times 10 to 11. For a Kevlar thread of cross-sectional area, that and that. Calculate the maximum break-in force. Right, so the breaking stress. So stress is, that's our force over area. And the breaking stress is 3 times 10 to the 9 pascals. We've got a cross-sectional area of 1.02 times 10 to the minus 7. So if we multiply, get rid of our area there, multiply that by 1.02 times 10 to the minus 7, then we're going to have our breaking stress. So that is, I mean, our braking force. That is, braking stress is the 3 times 10 to the 9, so that'll give us our braking force. So 3 times 1.02 is 3.06, and then we've got times 10 to the 2. We are operating at 3 significant figures here, so that's going to be fine, saying that we've got, well, that's 306 newtons. Also calculate the extension of the thread when the stress is 1.2 times 10 to the 9 pascals. Right, so Young's modulus is equal to FL over AX. So where this bit here is our stress, so the extension is going to be stress multiplied by length divided by Young's modulus. The stress they've given at 1.2 times 10 to the 9, the length they've given at 0.5, and Young's modulus they've given as, where was that, 1.3 times 10 to the 11. 1.3 times 10 to the 11. Okay, so this is going to come out fairly small. We've got 0.6 divided by 1.3 is 0.4615. So that's going to be 4.62. That's times 10 to the minus 1, 2, 3. 10 to the minus 3 meters. So yeah, just plug in everything into Young's modulus formula. So again, the calculations are, as they usually are with stuff to do with Young's modulus, are pretty straightforward. It's just plugging him into the three or four equations that we've got. So I suppose the main interesting part of this one is this idea of terminology. And this comes up in a lot of topics, really. You see people getting so confused about this. And actually, we have it in stuff to do with energy as well. You see the everyday use of words to do with energy gets mixed up. You know, people use energy and power interchangeably in everyday life. We have more specific uses for those words, more specific definitions when it comes to physics. But I think in materials, at least the way that it's handled before we go off to university, words like brittle, it's just not clarified enough. So these questions end up just sort of hanging in the air. Anyway, we'll leave that one there.